Let's start in the city roads above and work our way down to the hidden cities underground. Inside the road that sees and weighs you. Some roads don't just detect vehicles, they can estimate a truck's weight without stopping it. Rectangular asphalt cuts at intersections often hide an inductive wire loop. Current through the loop creates a weak magnetic field. When a metal object passes over, it alters this field, allowing a controller to detect the vehicle, count traffic, or adjust green light timing. Weigh and motion sensors convert each axle's force into a signal. Speed and axle spacing then reveal total weight. This shows the road isn't just a passive surface. These systems aren't on every street. Climate, road age, and past excavation change the layers beneath the asphalt from city to city. Heated streets. As shown here, electrical cables or thin heated fluid pipes sit beneath some roads, ramps, and sidewalks. Sensors trigger these heated pavement or snowmelt systems when moisture meets near freezing temperatures. Surface heat melts snow before it builds up or thaws thin ice. This works best on steep ramps, hospital entrances, and small critical areas. Heating a whole city would mean running a giant outdoor radiator, which is too costly to install, power, and maintain. The pavement layer cake. The asphalt we see isn't the whole road, only the top slice of a layered cake. A tire meets the surface course. From there, its load spreads through the binder course, base, or subbase, and compacted soil. Each layer spreads the force until it's no longer concentrated beneath one tire. Materials and thicknesses vary with heavy traffic, water, frost, and soil strength. Road renewals don't always remove the old surface. New asphalt may cover paving stones, buried streetcar tracks, or a forgotten old street level. So the first big surprise below may not be a pipe, but an old street. Utility spaghetti. What manholes really open into. Not every round street cover opens into a sewer. Identical covers may lead to a wastewater line, electrical vault, fiber connection, water valve, or steam main. Power and communications cables run through protective conduits. Access chambers at intervals let workers pull cable, make connections, or reach damaged sections. The surface cover is only a vertical entrance. Below, the network turns and continues horizontally. Writing on the cover may reveal the system, but markings vary by city. Its shape alone cannot tell you what is underneath. The pressure lines. Drinking water and natural gas may share a street, but don't need to run constantly downhill like sewers. Pumps or elevated tanks pressurize water. Think of a water tower as a gravity battery. Elevated water pressurizes the main, while service lines branch out. Regulators lower gas to the proper pressure between the main and buildings. Pressure lets both lines rise over obstacles, then descend. A water pipe may sit below the frost line in a cold state, but remain shallower in a warm region. Leaking gas can move through soil and voids, collecting in enclosed spaces. So no universal layout puts water here, and gas always above it. What hides beneath the sidewalk? The space under a sidewalk isn't just an empty route for cables. On some newly planted streets, cellular frames support pavement without compacting soil, giving roots room and briefly storing rainwater. In old, dense cities like New York, basements may extend into sidewalk vaults, where coal chutes and sealed entrances remain. Unused pipes often stay while new ones are added beside them, and old records may be incomplete or wrong. The city below isn't divided into neat textbook layers. It resembles a huge cable drawer not emptied in years. Each era leaves old lines and adds new pipes, cables, and spaces beside them. The gravity zone, where rainwater goes. A raindrop's underground journey begins with a road slope too subtle to see. Water follows the gutter and falls through a storm drain grate into a catch basin. A sump traps sand, leaves, and heavy debris, while a higher outlet feeds a storm sewer. From there, water may empty into a stream, be stored or treated, or soak into the ground. But not every city has a separate stormwater pipe. In older parts of American cities like New York and Philadelphia, rain enters a combined sewer carrying household wastewater too. Sewers must flow downhill. An ordinary sewer often runs on a slight slope. Wastewater moves from a building through a service pipe to the street main, which is rarely full so gravity can keep it flowing. As terrain changes, connections join, and the line extends, the main may grow deeper. Separate systems use different pipes for stormwater and household wastewater. Combined systems put both in one sewer. If heavy rain exceeds capacity, a mix of stormwater and untreated wastewater may discharge through overflow structures into a river or sea. Where gravity fails, a pump station lifts the flow to a higher line. Sewers are among the deepest common utilities under ordinary streets, but not the final depth. Buried rivers. Buried rivers are sometimes called lost rivers, though the water never truly disappears. As cities grew, small streams were enclosed in culverts or brick vaults, covered with fill and sometimes connected to sewers. But the old valley and low ground remain. We know because heavy rain can collect along the same route again, affecting basements and modern drainage. London's River Fleet is a famous example. Once an open natural stream, much of it now runs through enclosed drainage and sewer structures. It is neither an untouched underground river nor an ordinary purpose-built storm pipe. A city can cover the water, but it cannot erase the land the water follows. Deeper down, pipes carry more than water. The hidden city. Cities that move things with air. Futurama's tubes aren't pure science fiction. Some cities move solid material with airflow. In a modern vacuum waste system, or AVAC, trash collects in a sealed chamber. Central fans lower the pipe pressure. When a valve opens, waste travels to a station, where it is separated from the air, compacted, and loaded into a container. New York's Roosevelt Island is one of the few American examples and has used it since the 1970s. In the same city, metal capsules once carried letters between post offices through pneumatic tubes, pushed or pulled by pressure differences. Same physics, different cargo. One still collects neighborhood trash, while the other is a historical relic. Heating and cooling whole districts. Some pipes deliver heating or cooling energy instead of drinking water. Central plants distribute steam in parts of New York. Hot water circulates through a district heating network around Copenhagen. And Toronto uses Lake Ontario's deep, constantly cold water to help cool a separate closed loop downtown. What they share is that individual buildings don't have to produce all their own heat or cooling. A heat exchanger transfers energy from the network to the building. They may resemble city-sized heating or cooling circuits, but only make sense in dense, suitable districts. Tunnels you can walk through. Walkable utility tunnels combine several lines in a shared corridor people can enter. Electrical cables, water and heating pipes, and communications lines sit on wall racks. When something fails, crews can walk to it instead of digging up the street. But operating one is like running a second street underground. It needs lighting, drainage, ventilation, and fire protection. Construction is expensive, and space beneath city centers is scarce, so these tunnels are uncommon. Chicago's former freight tunnels and London's mail rail were also huge underground networks. But not every walkable network is a utility tunnel. Some were built for freight, mail, or passengers. Deep tunnels. 2 ways to build a subway. A subway's depth is often determined not by the train, but by how its tunnel was dug. Cut and Cover opens a street trench, supports or relocates pipes and cables, builds a concrete tunnel box, then restores the road. This partly explains why New York's early subways follow streets. Deep bore construction sends a tunnel boring machine horizontally through deeper ground. It doesn't swallow earth in one bite like a dune sandworm. It grinds the ground ahead, lays tunnel segments behind, and advances step by step. This disturbs the surface less and lets the route pass beneath buildings or rivers. Deep subways are impressive, but power and flood tunnels can go deeper. Power beneath the city. Power tunnels appear when the city above has no space for another cable. Instead of squeezing high voltage lines into crowded trenches, utilities place them on deeper racks. Because cables heat up, the tunnel needs ventilation or cooling. Crews reach connections on foot, heavy parts descend through shafts, fire compartments limit a failure's spread. Some London power tunnels pass beneath roads, railways, and the underground. It is a dedicated corridor electricity creates when near-surface space runs out, super sewers and flood tunnels. Super sewers and flood tunnels are enormous structures waiting not for trains, but storms. Yet they carry different things. When rain overwhelms a combined sewer, drop shafts send excess flow into a deep super sewer. It is stored until the storm passes, then sent for treatment. Flood tunnels instead move river water or storm water away from populated areas or into a reservoir. Chicago's TARP network, also called the Deep Tunnel, uses about 112 miles of tunnels and huge reservoirs to hold combined sewer flow temporarily. Outside Tokyo, a massive flood control system uses shafts and pumps to divert excess river water to another outlet. It isn't a sewer built for the same job. The largest tunnel under a city doesn't always carry people. Sometimes it waits silently to keep a few hours of rain or a sewer overflow from paralyzing life above. Enjoyed this style? Like and subscribe for more.